What's up, guys? Welcome back to the course. Just want to apologize for not being there in person today. I do not plan on asynchronous teaching often. It will happen once in a blue moon. This is one of those times. And hopefully you get a lot of this lecture. We are going to be covering the combination of resistors in parallel and in series, what that means to the resulting voltages and the resulting currents. Historically, students have done quite well in this section of the course. I hope that continues to be the case with this cohort. Okay. Resistors often have to be combined with one another, and so they can be combined in series, in parallel, or none of the above. First, we will consider the series connection case. This is the canonical picture that we will be dealing with. We have two resistors cascaded. So they are in series because they share the same current, which is here denoted by lowercase I. And they are connected to a battery, lowercase v. Now, we know from KVL that this voltage rise from B to A, or from here to here, this battery voltage V has to be dissipated across these two resistors. In other words, this V has to be equal to the sum of V1 and V2. Right, so that's another way of stating KVL. Going from the bottom left, voltage rise gets treated with a negative sign. Then the voltage drop of V1, which is the voltage drop across the first resistor, plus the voltage drop V2, which is the voltage drop across the second resistor. Right? So we know that V has to equal to V1 plus V2, which is the KVL equation. We also know from Ohm's law that V1 has to equal to the loop current I times R1. And similarly, V2 has to equal to I times R2. Notice that the current arrow is entering the positive terminal of these two voltages. So we can apply Ohm's law as is. So now let's combine those equations. Let's combine Ohm's law with KVL. If you substitute IR1 for V1 and IR2 for V2, you get that V, the battery voltage, is equal to the loop current times the sum of the resistors, right? And you can isolate for I. So now I is equal to V over R1 plus R2. In other words, the current, the common loop current is flowing through here clockwise, is equal to the battery voltage divided by the sum of the resistances in the loop. And what that means is that the equivalent resistance of R1 and R2 is equal to R1 plus R2. So when the resistors are in series, you add up their resistances and you can combine them into a single resistor, which we're going to call REQ. And this is a concept that will be brought up and employed time and time again in this course, the idea of combining resistors into a single resistor. And so this circuit here is equivalent to the circuit below. So we have that the battery voltage here is equal to I times REQ, where REQ is equal to the sum of R1 and R2. Okay, so for any resistors that are connected in series, you can combine them or reduce them to a single resistor whose resistance is the sum of the individuals. Very straightforward. So if you had n of these resistors in series, the equivalent resistance would just be R1 plus R2 ... plus Rn. And this brings us to voltage division. So notice that we know that V1 is equal to IR1, that's Ohm's law, and we know that V2 is equal to IR2, also Ohm's law. And so now let's substitute our expression for I into the Ohm's law equations. And what you get is that you no longer have I in the Ohm's law equation because you've replaced it with V over R1 plus R2. And so you get that V1 is equal to the battery voltage times R1 over R1 plus R2. Similarly, V2 is R2 over R1 plus R2 times V. And so what's important to note here and to understand is that these fractions here are always going to be between 0 and 1. So why is that? As I said last class, the resistance is always positive. It cannot be negative. It can be 0, but it can never be negative. And so if you have two numbers and you subtract and you divide one of the numbers by the sum of the two, you will always get a number that's bigger than 0 and less than 1. Right? So basically what you're doing here is you're splitting up this voltage into two parts. And the bigger the resistance, the bigger the part. And so, for example, if R1, well, let's take the simplest case. If R1 is equal to R2, then V1 is half of V and V2 is half of V. But if R1 is, let's say, 3 and R2 is 2, right? So we have 3/5 and 2/5, then V1 is going to be 60% of V and V2 is going to be 40% of V. Okay, so in other words, the voltage drops across a resistor in a series circuit is proportional to the resistance of the individual resistor. And so the battery voltage or the source voltage V is divided amongst the series resistors in direct proportion to their resistance. So in other words, the bigger the resistance here, the more voltage it sucks from the battery. Okay, now if you have n resistors in series instead of just 2, then the voltage drop across each of the resistors is going to be equal to that individual resistance divided by the sum multiplied by V. Okay, and remember, always these fractions are always between 0 and 1. What about resistors in parallel? So let's again apply our nominal laws. So law number 1 is Ohm's law, right? So we know that the voltage across R1 and R2 in this picture is equal to V. Why? Because V is in parallel to R1 and in parallel to R2. Okay, and the reason they're in parallel is because their top nodes are the same, node A, and their bottom nodes are the same, node B. And the current is going to flow out of the battery. Some of it will go down through R1, and the remainder will go through R2. And what we're concerned with here is how much of the total current I flows down into R1 and how much of it flows down through R2. And the answer to that question is precisely given by the current division technique, which we'll get to in just a few slides. Okay, so let's now write a KCL equation at node A. So right at this node here. So we know that I is equal to I1 plus I2 because current cannot be destroyed. And so we can replace I1 with the Ohm's law equation, which is V over R1, and replace I2 with this Ohm's law equation of V over R2. In other words, we have the total current I that comes out of the battery is equal to V over R1 plus V over R2. And so what it means is that you can factor out the V here, and what you're left with is that the battery current here, I, is equal to V multiplied by 1 over R1 plus 1 over R2. So notice that the equivalent resistance here is, or the reciprocal of the equivalent resistance is given by the sum of the reciprocals, right? So remember that Ohm's law is V is equal to IR, and that's why we put the REQ on the bottom here, because V over R has to equal to I, right? And so the equivalent resistance for a two resistor in parallel circuit can be written as the product divided by the sum. So how do we get there? Well, we simply perform basic algebra to this equation, common denominator, and then invert. And what that yields is that the resistance that this battery sees is effectively the product of these two divided by the sum. And that is interesting because if you take two numbers that are positive, multiply them, and divide by their sum, what you will see is that this REQ is always smaller than the smaller of these two numbers. And you will hopefully convince yourself of that property throughout the course. Okay, so the equivalent resistance of two parallel resistors is equal to the product of the resistances divided by the sum. So for example, let's say that you have two equal resistances, right? Let's say 10 and 10. So the product is 100 and their sum is 20. So the REQ is product over sum. So 100 over 20 or 50, or sorry, 5. And so 5 is less than 10. Like I said, it's always going to be smaller than a smaller number, right? So if the two resistances are equal, then putting them in parallel makes the equivalent resistance equal to a half. And so you can extend that rule to an arbitrary number of resistors in parallel. So if you have n resistors in parallel, the equivalent resistance, the reciprocal of the equivalent resistance, is given by the sum of the reciprocals. It's harder to say, I think, than it is to understand. At least I hope. So if you have n resistors, where all n are equal to each other, then the equivalent resistance is equal to R divided by N. So if you have, let's say, 10 ohm resistors in parallel, then the equivalent resistance is going to be 1 if they're all connected in parallel. Now, here's where conductance can prove a little bit useful, because notice that conductance is equal to 1 over resistance. So we can replace each of these reciprocals with a conductance. And then we have the conductance rule for resistors connected in parallel as GEQ is equal to G1 plus G2 dot 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 all the way through GN. Okay, so when you have resistors connected in parallel, the equivalent conductance of that network is equal to the sum of the individual conductances. Okay, so for example, you have this picture here. You have a whole bunch of resistors connected in series, right? And we are wondering what is, now we're going back to resistors in series. Needs to be pointed out here. And we write them, instead of R's, we write them with G's. So resistor 1 is labeled with its conductance G1 and so forth. And so what is the total sum of these, what is the GEQ here? What is the equivalent conductance of this series combination of resistors? Well, it turns out that when the resistors are connected in series and you want to combine them in terms of conductances, you apply the reciprocal rule, namely 1 over the equivalent conductance is equal to the sum of the reciprocals of the individual conductances. So you would not normally do this, but we point this out to kind of show the duality between series and parallel and resistance conductance. Okay, now going back to our original circuit where the two resistors are in parallel, and I apologize for the flip-flop. Again, to reorient you, we are back to the original current divider circuit where you have current splitting into two paths. And we want to derive an expression for I1 and I2 in terms of I. So we know that the equivalent resistance is equal to the product divided by the sum. We also know that I1 is equal to the battery voltage divided by R1. And so the battery voltage is equal to this expression here. And now if we divide that by R1, you cancel out this term here that I'm scrolling my cursor across, and you're left with R2 over R1 plus R2 times I, which is the equation here. Similarly, current I2 is equal to this expression divided by R2 because of Ohm's law. Ohm's law says that I2 is equal to V over R2. And so what you're left with here is I1 times R1 over R1 plus R2. Notice what's happened. The current in branch 1 is proportional to the resistance in branch 2, whereas the current in branch 2 is proportional to the resistance in branch 1. So it's the opposite of what we saw with resistors in series. Namely, the current that flows down this branch is given by R2 over the sum of the resistances times I. And the current in this branch is given by R1 over the sum of resistances times I. So this is another case where we see that current follows the path of least resistance. Namely, if R1 is very high, so if R1 is much bigger than R2, then the current will want to avoid R1 and go to R2. Whereas if R2 is much bigger than R1, then the current will want to avoid the outside path and take the inside. Okay. So the current is shared in an inverse proportion to their resistance. That's current division. So circuits with parallel resistances are often called current dividers. And again, the larger current flows through the smaller resistance. And by the way, I should have probably stated this a few slides ago. Circuits with series resistances are often called voltage dividers. So let's now take the extreme case where one of the two resistors in parallel is equal to 0. So we have a short circuit here. So this is normally where I would ask the class, what is going to happen in this picture? And what ends up happening is that the current avoids R1 altogether because it has a clear path for the exit right around the corner, right? So this current I, it has a choice of going through R1 or going through R2, but R2 is 0. So all of it will go on the outside. So in other words, the I1 is going to be equal to 0, and I2 is going to be equal to I, the total current. And so what that means is that the equivalent resistance, which is equal to product over sum, is equal to 0, because the product is 0, and the sum is equal to R1. And so all of the current flows through the short circuit. Now, what about the other extreme, where now the second resistor is an open circuit? So in other words, it has an infinite resistance. So what happens in this case? Well, here, all of the current will go through R1 because it will avoid the infinite resistance of R2. Okay? And again, if you take the limit of this as R2 goes to infinity, you get that REQ is equal to R1. And so you can show this just by basically noting that as R2 gets bigger and bigger and bigger, this fraction tends to R1. That's the limit. And so in other words, the equivalent resistance of a current divider where one of the resistors is infinite is equal to R1. It's as if this branch just doesn't exist. Okay. This slide is not as important, but I will go through it, but I'm just going to footnote it because we don't often do this in this course, but it is technically part of the material. How does current division work in terms of conductance? So same idea, you have a current I that's split up into I1 and I2. And we label the resistors with their conductances now. Right? So if we divide both the numerator and the denominator by R1 and R2 of our canonical, this is just what we learned previously, that I1 is equal to R2 over R1 plus R2 times I, and I2 is equal to R1 over R1 plus R2 times I. This is what we know from before. Now, if you multiply both top and bottom by R1 and times R2, you get the following equations, namely I1 is equal to G1 over G1 plus G2 times I, and I2 is equal to G2 over G1 plus G2 times I. So this looks a lot like voltage division in that the bigger the conductance, the more current it draws. And so in general, if you have n conductors or resistors in parallel, then the nth conductor will have a current of Gn over the sum of the G's multiplied by I. And so again, hopefully you're seeing this duality between voltage division, current division, series, and parallel, resistance, conductance. Okay, now we move into the examples portion of this lecture. So the first thing we're going to do is just do some combining of resistors. So usually at this point in the course, what I tell you guys is when you're given a question such as this, so you're asked to figure out the total resistance of this network of resistors when looking from the left. Okay, so you're looking from the left. So I generally advise you to start your simplifications on the right. Okay, so for example, the 1 ohm and the 5 ohm can be reduced to a 6 ohm, right? Because they're in series. The 3 ohm and the 6 ohm are in parallel. So product over sum is 2. Right? So next step is we combine the 1 and the 5 into a 6, and we combine the 3 and the 6 into a 2. Right? And notice that we've replaced this parallel branch with a single 2 ohm resistor, and we've replaced this series branch with a 6 ohm resistor. Everything else stays the same. And now again, 2 plus 2 equals 4. So that's 4 ohms over here, and that's in parallel with 6. Right? So 4 in parallel with 6, 24 divided by 10 is 2.4. And then 4 plus 8 plus 2.4 gives us 14.4 ohms. So you can do this in any order you want. As long as you apply the laws properly, correctly, you will get to the same correct answer. Okay, let's go to the next example. So again, I urge you to start from the right side. So we have, my Zoom window is blocking, here we go, 4 ohms plus 5 ohms plus 3 ohms, that's 12, right? So we have a 12 ohm over here, and everything else has stayed the same. So 4 and 12, that's 4 times 12, divided by 4 plus 12, that's equal to 3. You'll start to memorize these after a while. So the 4 and the 12 in parallel reduced to a 3. Okay, so this 3 ohm resistor has replaced this parallel branch. And now we have a 6 ohms here because 3 and the 3 are in series. So they can be reduced to a 6 ohm resistor. And now the 6 and the 6 are in parallel. So whenever you have two resistors with the same value in parallel, you just half the value. You get 3. So 2 and 3 and 1 all in series gives you 6 ohms. Okay, so again, this is the part of the course where students generally have done well. This is intuitive. Now here is one that's a little bit different. And although it looks complicated, as long as you keep your terminals connected according to the original circuit, you're fine to redraw it in a way that's probably easier to look at. Okay, so the first thing that we're going to do is easy, actually. We're just going to reduce the 1 and the 5 into a 6. Everything else has stayed the same. So here's the big step, right? So notice that the 6 and the 4, first of all, have been transformed to a 2.4. So that part is straightforward. We have these two resistors have been reduced to a 2.4. Now, the thing to look out for is what has happened to these two diagonal electrodes. So let's focus on the 6 ohm. The 6 ohm is connected to the juncture between the 10, the 3, and the 1, right? And the bottom of it is connected to the bottom node. So as long as the top of the 6 ohm is in this juncture between the 10, the 3, and the 1, we can draw it as is. Notice that the position of the 6 ohm circuit here is electrically equivalent to its position over here. Why? Because the top and the bottom connections are all at the same node. Similarly, the 12 ohm resistor has its top node in between the 1 and the 4, right? In between the 1 and this used to be the 4. It was reduced to a 2.4. And its bottom is the bottom node. It was going to be known as the ground soon enough, right? So again, we can redraw the 12 ohm resistor kind of in a vertical manner, just by making sure that its top node is connected to the back end of the 1 ohm resistor, and that its bottom node is connected to the bottom of the circuit, was going to be known as the ground. And so now that we have it redrawn in this form, it becomes more straightforward. We can combine 12 and the 2.4 in series, and that gives us 2 ohms. And we can combine the 3 and the 6 ohms in parallel. So 3 times 6 divided by 3 plus 6 is 2 ohms. Right? So now we're getting down to the end. The 1 and the 2 combine into a 3. The 2 and the 3 combine into a 1.2. And the 10 and the 1.2 combine into an 11.2. So again, just make sure that as long as you can maintain your connections of every resistor, you can redraw it in whatever shape you want. All right, another one of these kind of bridge type looking networks. First thing we're going to do here is to, let's see. What's the first? All right, so what we done here is combine the 20 and the 5 into a 4, because 20 times 5 over 20 plus 5 is 4 ohms. And this parallel connection here of 4 ohms equivalent is in series with the 1 ohm. So that's 4 ohms here and 1 ohm here, corresponding to the 5 ohms over here. Now, the 20 ohm has now been redrawn to be vertical, right? And how have we known to place it here? Well, the bottom node of the 20 has to hit the front of the 2 ohm resistor, right? And I say front because, imagining that the current is flowing clockwise, current hits this part before exiting here and go to terminal B. And how do we know to put the top of the 20 here? Well, notice that this node here is the node in between the 8 and the 5 ohm equivalent resistor that is formed by the combination of the 20, the 5, and the 1, which is here. Right? So notice that the top of the 20 ohm resistor is in between the back of the 8 and the front of the 5, just like it's drawn. Okay, and everything else so far has stayed the same. We've kept the 18 ohm diagonal resistor as is. And what we're going to do, as you can guess, is that we're going to reduce the 20 and the 5 into a 4. And then we're going to reduce the 4 and the 2 into a 6 and make that in parallel with a 9. So 6 times 9 divided by 6 plus 9 is 3.6. And now it's easy to see that the 18 ohm resistor can equivalently be drawn as being parallel to all of this that I'm highlighting. Right? Why, and how do we know that it's in parallel? Well, first of all, they share the top node. So the top node is the same. And they share the bottom node once these three are simplified together. Right? So the bottom node of these three is over here, which is the same as the bottom node of the 18 ohms. So we can just straighten out the 18 ohms while preserving the connections of this circuit. And at this point, you can combine the 18 with the 3.6. So here you probably want to use your calculator, product divided by sum. And then that gives you an equivalent resistance of 3, which is added to the 8, which is added to the 3, giving you 11 ohms. All right. So now we have an example where we are asked to find the equivalent conductance, right? So same as before, but now instead of specifying resistances, the resistors are labeled with their conductances G. So the laws flip. So for example, the 8 and the 12 can be combined as 8 plus 12 Siemens, right? So 8 plus 12 gives you 20. That's a measure of conductance. So the 5 and the 20 have to be combined using the reciprocal rule. 1 over 5 plus 1 over 20, and then I'll reciprocate it again. That gives you 4. And then the 6 and the 4 are in parallel, which means that we can add them. So we have a final conductance of 10 Siemens. All right. So again, the laws just flip here. So notice that the 8 and the 4 here are in fact parallel because they share the same top node and the bottom node. So they can be reduced to 12s. Okay, so the 12s is now in series with the combination of a 2 and a 4. So how do we get this 4? Notice that the 6 and the 12 are in series because any current that flows through the 6 has to also go through the 12. So 6 and 12, using the laws of combining series conductors, is 1 over 6 plus 1 over 12, again reciprocated. So that gives us 4. So now we have 2 and 4 in parallel. So that can be reduced to 6. And then we have 12 and 6 in series, which can be reduced to 4. So again, just remember that if you're asked to do this in conductances, the laws for series and parallel combinations just flip. All right, 2 more examples before concluding this lecture. It may actually be 3, I can't remember now. So we are asked to find I naught, that's the current here, V naught, that's the voltage across the 3 ohm resistor, and the power dissipated in the 3 ohm resistor. So oops, I didn't want to advance it. So you have to think about what can you do to make your life easier. So how can you figure out the I naught here? Well, you know that this current I is going to split into 2 parts. The part that flows across the 6 and the part that flows across the 3. And so what you're going to want to do is figure out what that I is, first of all. So notice that the 6 ohm resistor and the 3 ohm resistor are in parallel. And so they can be reduced to a single resistor whose value is 2 ohms. Right? So you have 12-volt battery, the 4 ohm battery, the 12-volt battery, the 4 ohm resistor here, and the 2 ohm resistor, which is really representing these two resistors in parallel. Right, so the equivalent resistance of the circuit is 4 plus 2, which is equal to 6. And so what that means is the total current, right, that's flowing through the circuit is 12 divided by 6, which is 2 amps. So so what you can do, for example, is take know that I is equal to 2 amps, apply the current division rule, and figure out how much is flowing through the 3 ohm resistor, and then that gives you I naught. But an easier way is to apply voltage division directly to this picture, right? So this is the picture that you want if you're looking to apply voltage division, because you have a voltage, a source voltage that's connected in series to 2 resistors. So we know that 2/3 of this voltage are going to be dissipated across the 4 ohm, and the remaining third will be dissipated across the 2 ohms. And so that 1/3, that remaining third, is given by 2 over 2 plus 4. And that's how you get this. The 6 here, it corresponds to the 4 plus the 2. So the V naught, which is the voltage across this 2 ohm resistor, which is really this voltage here, is equal to the 12 times 2 over 2 plus 4, which is equal to 1/3 of 12, which is 4 volts. So now you know that the voltage across the 3 ohm resistor is given by 4 volts. So to get the current, you just take the 4 and you divide it by 3, and you get a current of 4/3 of an amp through the 3 ohm resistor. Okay, so the last thing that's remaining is to figure out the power dissipated in the 3 ohm resistor. So probably the easiest way is just to multiply these two answers, because we know that power is equal to voltage times current. So, well, I actually did it by squaring the voltage and dividing by 3, which gives you the same answer as if you would have multiplied these two numbers together. You get 16/3 of a watt. So before I move on, I want to be sensitive to the fact that you do not have the ability to ask me a question. So I think oftentimes people get confused as to what happens here, right? This 2 ohm resistor is really representing these two resistors that are in parallel. Okay, so a trick that is often used is we combine resistors, we find their equivalent resistance to get, a voltage or a current, and then we can expand the circuit back out to figure out, for example, the value of I naught. Right, so that's what we did here. We got the voltage from voltage division. We figured out that 1/3 of the battery goes to this part of the circuit. And then we applied it to the original circuit, the unsimplified, to get the current of 4/3 of an amp. All right. Next example, we are asked to find V1, V2, I1, I2, as well as the power dissipated in the 12 and 40 ohm resistors. Okay, give me 1 second here. This is no Khan Academy. I take water breaks. Thumbs up if you like this video. Okay, V1 and V2. Right, so again, what we want to do here is notice that there are two sets of resistors, two pairs that can be reduced, right? So the 12 and the 6 are in parallel, so they can be reduced into a 4. And the 10 and the 40 are in parallel, so they can be reduced to an 8, right? So this circuit can be redrawn as 15 volts in series with 4 ohms in series with 8 ohms. Right? And so how does that help us? Well, it helps us because now we know the voltage is V1 and V2. So V1 is still the voltage between this point, and V2 is still the voltage between this point and this point. So we want to apply voltage division, right? So the voltage V1 is equal to 15 times 4 divided by 4 plus 8, which is equal to 12. So in other words, because the 4 ohms is 1/3 of the total resistance in the circuit, we know that it draws 1/3 of the 15 volts, which is 5 volts. And V2, you can just use KVL. So 15 minus 5 equals to 10. So if there's a 15 volt rise and a 5 volt drop, we know that there has to be a 10 volt drop across the 8 ohm resistor. Now, what about I1? Well, I1 has to equal to V1 divided by 12. We know that V1 is equal to 5. In other words, I1 has to be equal to 5/12 of an amp, which is approximately equal to 417 milliamps. Similarly, I2 is going to be equal to V2, 10 volts, divided by 40 ohms, which is 1/4 of an amp, or 250 milliamps. And finally, how do we get the power dissipated in the 12 ohm and the 40 ohm resistor? Well, one way is just to take the voltage and square it divided by the resistance. So V1 squared over 12 is equal to 25 over 12, or a little bit more than 2 watts. Similarly, P2, that's the power dissipated in this resistor, is equal to V2 squared, or 100 divided by 40, so 2.5 watts. So again, the same kind of logic applies. We reduce the resistors, so to a single resistor here and here, to draw this circuit. And then we apply a simple voltage division rule to get the voltage across the 4 ohm, which is really all of this, and the voltage across the 8 ohm, which is really all of this. And once we have those voltages, we can apply them back to the original circuit to get I1 and I2. Okay. Last slide. Determine A, the voltage V0, which is here, the power supplied by the current source, and the power absorbed by each resistor, right? So again, notice that we have a circuit that can very much be reduced, right? The 6 and 12 are in parallel, are in series, sorry. So they can be reduced to an 18. And then that 18 is in series with the 9K. So we have 18 kilo ohms on this branch, the outside branch, and 9 kilo ohms on the middle branch. And we still have the 30 milliampere current source. So we're interested in finding the voltage V0, which is the voltage across the 9 kilo ohm. So here, this is the classical case, the classical scenario for applying current division. Remember, this resistor occupies 1/3 of the total resistance. And this resistor occupies the 2/3 of the total. So in other words, this resistor will draw 2/3 of the 30, and this resistor will draw 1/3 of the 30. Mathematically, we can see this by reducing the 9 and the 18 together, forms a 6. So 9 times 18 divided by 9 plus 18 gives us 6. And so now let's apply our current divider rule, and we get, so this is the 30 milliamperes here, that's multiplied by 18 and divided by 18 plus 9. And that's equal to 2/3 of 30 milliamperes, which is equal to 20 milliamps, which is equal to the current that flows down here. That's equal to I1. So remember that I1 is equal to the 18 divided by 18 plus 9, so that's the 2/3, multiplied by the original 30 milliamps. And we know from Ohm's law that V naught has to be equal to I1 times 9 kiloohms. So I1 was 20 milliamps. Multiply that by 9 kiloohms, and we get 180 volts across the 9 kilo ohm resistor, which is V naught. Okay, so we have our answer for V naught. Now we need to know the power supplied by the current source. Well, remember that power is equal to current times voltage, right? So the current is equal to 30 milliamps, and the voltage is equal to 180 volts, right? Because the 9 kilo ohm resistor is in parallel with this current source. So we just need to multiply 30 times 10 to the minus 3 by 180. That gives us a power of 5.4 watts for the current source. And now we also need to figure out the power that's absorbed by all three of these resistors. So there's many different ways of doing it, at least three, right? So, but before that, we need to know what I2 is, right? So I2 is equal to the 30 that comes into here minus whatever flows down the 9 kiloohms, right? So we know that, we know that 20 goes here, so the remaining 10 has to go on the outside. In other words, I2 is equal to 10 milliamps. And so the power of the 9 kilo ohm resistor is equal to V naught squared divided by 9,000. V naught is 180 volts, and 9,000 is the 9 kilo ohms corresponding to its resistance. So again, remember, one of the equations for power dissipation is voltage squared divided by resistance, which in this case gives us a power of 3.6 watts. Now moving to the 6 kilo ohm resistor, we know that its current is equal to I2, which is 10 milliamps. So another equation for power is I squared times R. So I squared is equal to 0.01 squared times 6,000 ohms gives us 0.6 watts. So if we have 5.4 watts being generated by the current source and 3.6 dissipated by the 9 kilo ohm resistor and another 0.6 dissipated here, what's left is 5.4 minus 3.6 minus 0.6, which is equal to 1.2. And another way of getting that 1.2 will be just to apply power is equal to I squared times R, which is equal to 10 milliamps squared, so 0.01 squared times 12,000, which gives you the same answer of 1.2 watts. I will start off with the Wednesday lecture, but I'll allot a given amount of time to take questions from you guys on this material, just so that none of you gets shafted by the inability to ask me questions during the live lecture. With that, I hope that you enjoyed the lecture. Please remember to give it a thumbs up. The merch is coming, and don't forget to subscribe to my channel.